So we were talking on Friday. We started talking about piecewise functions, right? And so we had just kind of gotten into dealing with how we graph these things. And brief review, the way we want to think about this, we're going to have as many kind of regions in our graph as we have pieces in our piecewise function. And at least in your mind, you don't necessarily have to do this on the graph, but at least in your mind, you kind of want to think about these as being sectioned off by these vertical lines that are sort of boundaries. The vertical lines are not part of the solution, right? They're just there to kind of partition off the parts that are going to be the piece one versus piece two versus piece three, okay? So we were focused on this piecewise function, and we were graphing the first piece, which was f of x equals the function 2x, the line y equals 2x, whenever x is less than or equal to negative 2, right? And what we said was, then we'll just put a vertical line at x equals negative 2, and every place to the left of that is our red region. We color-coded these, right? That's the region for that first piece. Well, it's just a line, and so we only need 2 points to define a line. So we just need to define 2 points in that region so we could connect and extend and graph our line. We had just talked briefly about why, normally if we have the line y equals 2x, we would just graph that with a y-intercept and a slope, and it's super easy to do, right? But that's not convenient for us here because the y-axis is not included in that region. So those aren't convenient points for us, right? So instead, we want to pick convenient points in our region. And you guys correctly told me, you had good insight here. You told me that one really good point to pick is the ordered pair -2, -4, because that's the one that's on the boundary. And doesn't that make sense, right? If we're going to pick 2 points, we'd like to have one that's over in the region and one that's on the boundary. So when we graph our line, we know where that one stops, right? Where the ant has to make a transition as the ant is walking along this graph, where he has to make a transition from red to blue, right? At the endpoints. Okay, give me 1 to 5 on that summary. Is everybody up to speed on that summary? Does that make sense to you where we left off on Friday? Okay, how are we doing? Okay, good. And it just takes a second to get used to this. We'll go through a couple examples. What would be another point we could pick? Just a convenient one. It doesn't matter. Like, throw one out. What's another x value we could pick here? Does this seem like a reasonable one if I pick -4, for example? That's all right, isn't it? That's not giving us, I wouldn't want to pick one, like, what would be wrong with picking -10? Yeah, it's too big. Like, it's way off the graph vertically. We don't want to do something like that. We want to pick one that's relatively convenient, just a practical consideration, not a math consideration, just in terms of just graphing this thing. So if I evaluate my function, if I plug -4 in for x, what do I get for y? -8, right? Does it make sense if I talk about evaluating? Let's just take one quick second here. If I talk about evaluating the function, so f of -2, when you look at the piecewise function, does it make sense that that would be -8? Can somebody tell me how they would look at this big mess of a piecewise function and come up with that same answer? Because you're right, it is -8. And I'm guessing a lot of you guys were looking up here at this equation when you said that, right? Because that's the line we're graphing. How would we look at the piecewise function and get the same answer? What's your thinking on that if I'm inputting a -2? What do you think? There's multiple pieces, so how would we deal with that? How do we know which piece to input -2 into? Okay, yeah, which one does it fit into in the domain, right? Does that make sense? Okay, so if I'm plugging -2 in, you got to ask yourself, which of these domains does that fit into? Well, it's going to be the red one, right? Because -2 is less than or equal to -2. So that whenever you're evaluating a piecewise function, that's always going to be step one. where do I, which row am I plugging that number into? And then it's easy. Then it's just like a regular evaluation problem. When we know it's row 1, we plug it in. And so we would just get 2 times -2 equals, well, I plugged in -2, I guess. I meant to plug in -4. But you get the idea. 2 times -2 is -4. And that's how we would have gotten our -4. Okay? All right, so then we have 2 points. Now all we have to do is just connect and extend. So I need to grab another point. This is going to be, obviously, this is going to be a closed point because it's inside the interval, right? The only place where we could ever have an open point would be at an endpoint. Okay, but ours wasn't in the first case. So -4, we said -8 is right there. And then I would just connect and extend. Do I have? No, I don't. Oh, okay. Yep. There you go. You're right. I was thinking that was 10. There we go. Okay. And then something like that. Everybody good? All make sense? So there's our first one. Okay. What about the next region? There's our first one. Next region, let's see. So that's the blue region, right? Where x is greater than -2 and less than 4. So here's our blue region. Again, we just need 2 points in the blue region. Which 2 points should I definitely choose this time? -2 and 4, right? I want the boundaries. I want to know, where is this thing starting and ending? So let's try -2. If I plug -2 into the function, into the blue function, and now in the blue region, we've got this function, right? We've got the line y equals -1 minus x. So if I'm plugging in -2, what do I get? Yeah, 1, isn't it? Good. So -1 minus -2 would give me +1, wouldn't it? So I get that point. Okay, now, is -2 actually included in the blue region? What region is -2 actually in? The red region. Why did we pick -2 again? Because it's a boundary, right? That might seem a little confusing. Technically, I really couldn't plug that in and say it's a part of that region, but I know it's an endpoint, okay? So what kind of an endpoint am I going to use here to communicate that? That it's not technically in that region, but it is the boundary or the endpoint of the blue region? Open, yeah. So at -2, 1, I want an open endpoint. -2, +1, there you go. And then we'll do the same thing you already told me for x equals +4. What's -1 minus 4? -5, okay? So there's my other endpoint. Open or closed? Open. Okay, again, because 4 is actually not included in the blue region. It's just an endpoint. So we say that was 4, -5, okay? There we go, okay? And then all of the infinite points that actually are included in the blue region would just be the ones on that line segment that connect the endpoints, right? Okay, so we get that. Okay, give me 1 to 5 on that. How are we doing? Is that all making sense? Okay, then the last part, green region, that's every place greater than or equal to 4. Throw out 1 endpoint for sure, or 1 point for sure. I kind of gave it away. We want to use 4. Is 4 included in the green region? It is, so we're going to end up having to have a closed endpoint. If I plug 4 into my function, what's the output? In fact, what's the output always going to be? -3. Doesn't even matter what the input is. The output is -3. What kind of line do you expect the green line to be? Straight. Well, they're all straight. What do you mean by straight, though? Every line's straight. What is it? Vertical? Agree with that? If the y value is always -3, okay, that makes it horizontal, right? Because the y value stays the same, regardless of what x value we put in. So then we would get, for example, the point 4, -3, and really picking another point is, it's almost kind of unnecessary here, isn't it? You know we've got one at 4, -3. It doesn't matter what other x value I pick. The y value is guaranteed to be -3. So take your pick. We'll just throw in 8, which is at the end. Not that it matters. End of our graph, at least. Okay, tell me about open or closed on those points. Closed. Okay, both are closed. Good. Yeah, -3. Okay, so we got a point there we graphed and a point there. And then it just goes forever to the right, doesn't it? So that's our graph. Okay, there's all three pieces. So later on, when we start talking about, we'll mention these words this year, but when we get into calculus, we'll talk a lot about this stuff. We would say that this piecewise function is discontinuous at -2 and at +4, because those are places when I graph the function where I would have to pick my pen off the board. So any place where we have to pick our pen off the board to graph something or off the paper, those are discontinuities. Okay, again, that's really not an algebra 2 issue so much, but a big issue in calculus. Next step, domain and range. Okay, so remind me, now we haven't talked a lot about domain and range yet, but I want to just start thinking about it now. We're going to look at that in more detail. Let's see. Well, you guys talked a little bit about this, didn't you? Because that was stuff when I was gone. You guys watched a video about that, correct? Didn't you? Yeah. Okay. So we have. So I wasn't here, so I'm not remembering that right. But you guys have technically seen this stuff. So help me out with that. Domain and range. What is the domain? How do you define that? The set of all what? X values, or just in general input values. Usually X, because that's usually our input, but it doesn't have to be. Whatever our input variable is, that's the domain, the set of all those values. So looking at this graph here, what is the set of all input values? All reals, yeah. You're just kind of really asking yourself, okay, which values are excluded? And there aren't any. Every value is included. In other words, if we think about this in terms of the ant again, as the ant is walking along this function, the ant always has solid ground to stand on. There's always an x coordinate for the ant to stand on, right? He's never falls through anything. He's always got a place to stand. So domain, all reals. Okay, the range, what is the range again? Define that. Y values, set of all the y values or the outputs, whatever, usually y, doesn't have to be. So what about the y values? Now that doesn't really look like that is necessarily all reals, does it? Okay, we want to find all the possible y values that the ant could step on. Say it again. Less than 1 is the right answer. Yeah. Okay, does everybody see that? That's a little tougher one to see. Give me 1 to 5 on that. Do we see that that's the... Okay, that's pretty good. I mean, that you guys see that so quickly. One way you can always think about this, I'll just show you something that's kind of a cool thing in math, because again, this isn't so tremendously important now, but in the future, you guys will talk about when you're in college, you'll talk about projections. Like like for example, you might project, here's an example of a projection. You could take a 3-dimensional space and project that information into 2 dimensions. How in the world you guys have all seen this before, actually. Have you ever seen a situation where 3 dimensions are projected onto a 2-dimensional piece of paper, for example? Yeah, TV. Well, okay, true, but with a TV, you don't really have all the information there. Like a map, exactly, like a topographical map where they've got lines of altitude and stuff. So you actually have the information on there for that 3rd dimension, which is height, even though you're only seeing 2 of the dimensions on the map, right? So something like that. So you'll do projections, more in the future. Here's just kind of an introductory idea about projections. What if I took each of these three pieces and projected those onto the y-axis? Because that, you guys told me the range is the set of all y values, right? If I took the red piece and projected that onto the y-axis, wouldn't it just look like this? Like this point's going to project over to there, that point right there is going to project over to there, and so on. And it would just fill in that whole part of the y-axis, agreed? If I projected it or just squeezed it onto the y-axis. What if I did the same with the blue? Well, the blue is going to have a top value, a maximum value of 1, but it's an open endpoint because 1 actually is not a y value that's included. And then it would go all the way down to whatever that is, -5, but those are already graphs, so I don't even really need to put that open endpoint in there, right? Those are already part of my range. So it's just going to add all the pieces, all the y values that are greater than -4 and less than 1. And then the green range, if I project that, well, that's already a point that's in the range also, so it doesn't really contribute anything new. Okay, make sense? All right, so then our range, we would say as if I'm using interval or an inequality, I would say y is less than 1. Using interval notation, what would that look like? With what kind of parentheses? There we go, perfect. Okay, good. All right, you're getting this stuff really quickly. That's good. That's good. Okay, let's see if we can just zip through one of these. Well, I don't know. What do you think? Do you want to go through another one of these? One more, maybe good idea? Yeah, let's go through one more. Okay, what about one like this then? Let's just kind of go through the steps. Go through the steps here. What's my first step, at least in my mind, that I'm going to do? Yeah, I want to break it into regions. Where are my boundaries going to be, the vertical lines? 0 and 6. Okay. So there and there. Okay. And then based on those boundaries, we'll split it up into regions, right? Now, and again, you guys don't have the luxury of color coding this, but up here we do. So here's going to be the red region. That's the top, essentially that's the top pieces region. Here's the middle pieces region, which is blue for us, and then the bottom pieces region, which is green. We need to pick some convenient points. So what would points be? Pick a couple for me in the top region. 0 would definitely be a good one. If I plug 0 in for x, what do I get for y? 0, right? Yeah, exactly. Exactly. Because the top equation is y equals -3x. So -3 times 0 is 0. Open or closed endpoint? Open. Yep. So we get an open endpoint at the origin. Give me another convenient point. -2, -1. You pick. I mean, any of those would be fine. So how about -2? That looks good. We got 2 ordered pairs. -2, 6, open or closed? So what would it be? Definitely closed, right? It doesn't even make sense to almost ask that question because that's a point that's inside the region. So of course that's a point that's on the line, right? Open endpoints or open points would only make sense as possibly at an endpoint, but that's it, right? So then -2, 6. Whoops. That gives us point -2, 1, 2, 3, 4, 5, 6 right there. Okay. And I could just graph this guy. Let me see if I go to the next page. Oh, never mind. I can't do that. Okay. So there's my red piece. Blue piece. What would my 2 points be that I'd want to select here? 0 and 6. If I plug 0 in, and let's go ahead and write down the blue equation. Blue equation would be the line y equals -1/2 x minus 1. If I plug 0 in, what do I get? minus 1. If I plug 6 in, I get -4. Good. So there's my 2 points. What are the endpoints like here? At 0, closed. Okay, so 0, we've got, what was the point again? 0, -1 was closed. Six, -4 is open. Okay. And then I just have to connect those two with a line segment. So there's the graph of the blue piece. Okay, good. Give me thumbs. How we doing? Okay, how about the green piece? Green piece, endpoints, or excuse me, what would my values be? What's one I'd pick for sure? 6. Okay, if I plug 6 in, let's write down the green equation. Y equals x minus 7. If I pick 6, what do I get? -1. What would be another one be? How about 8 would work, right? If I plug 8 in, I just get +1. And what's the nature of the endpoints here? Okay, open, and then there really isn't another endpoint. Good, so open at 6 and just a regular point at 8. Okay. So there's my graph. Looks good. Let's get domain and range now. What's my domain this time? Is it? Is it all reals? Okay, everything except 6. Yeah, right. There is a place where the ant can't stand because I have both of the boundaries at 6 in the blue region and the green region are open endpoints, right? Neither one of them is included. So how do I say that? Well, the domain, there's a couple ways I could do this. If I want to write this using an inequality, the easiest way, honestly, is just to say x is not equal to 6. Right? If I say that, that implies that everything else is fine, but x cannot equal 6. That's the way we would probably write it in calculus. Now, if they really want you to write that using an inequality, where I can't just say a not equal sign, how would I have to write that as an inequality then? Yeah, either x is going to be less than 6 or x is going to be greater than 6. It can be any other thing, but it just can't be 6, right? So that's the other possibility. X is less than 6 or x is greater than 6. How would I say that with interval notation? Oh, by the way, on the last one, we didn't do this on the last one, but we could have. Oh, what happened here? There we go. How could we have said all reals with interval notation? Negative infinity to positive infinity, because it would have been the entire axis. So the left endpoint would have been clear out at negative infinity, right point at positive infinity. So yeah, we could have said that. Okay, so how about this? Did I delete something? Or?
No, I think you have to go forward. Like not one, but two.
Go one more?
Yeah.
Oh, there we go. Okay. So what would the domain be here then if I wrote that with intervals? How would I say x is less than 6 with intervals? With parentheses on both. Good, because I'm not including either of those endpoints. What's my, oh, there we go. What's my or like, Bree? Like a u. There you go. Okay, so I got a u. And then over here, I've got 6 comma infinity with parentheses. Good. Okay. How about the range then? We haven't dealt with the range yet. So if we project all this stuff onto the y-axis, Everybody agree we're going to get from the red piece, we're going to get this, right? How about from the blue piece? What's that going to look like as a line segment on the y-axis? Okay, it's going to go from -1 down to -4. What kinds of endpoints on that one? Okay, open on the bottom, closed on the top at -1. Everybody agree? So it's going to look like that. Here, let me color in the middle just so we can see. Oops. Like that, right? And then finally, the green one, what does that do? Okay, open one at -1, but whoops, there's already, that point's already a y value that's included, right? That's already part of our range. Everybody agree? So that open one doesn't really contribute anything. There's already a closed endpoint there. And then what does it do? What does it effectively do to our range? Oh, yeah, because it's going to fill in everything above that, isn't it? Right. If I superimpose all these points, that one right there is going to fill in that open endpoint, and then the rest of it just overlaps, doesn't it? So that's our range. Okay, so how would I say the range as an inequality? Okay, what's greater than -4? Y is good. Say that as as interval. Whoops. -4, comma, infinity, and I'd need parentheses, right? Okay, good. All right, let's turn this around. So now I'm giving you a function, and I'd like you to tell me the domain. I want you to write the piecewise function, right? So you can also say that as give the rule, meaning what are the equations for the individual pieces, or just write the piecewise function and give the domain and range. So let's kind of color code this one too. How about if we make this first one red? Okay, how am I going to write that red piece? That's going to need a row. It does, yeah. Here, let me make that more clear too. Blue one has an open endpoint, so there. That's a little better maybe, huh? So the red piece, how would I write that? Okay, so let's start with the domain. That's a good idea. Let's scoot over to the right, and for the red piece, let's start with the domain. The domain is x is less than or equal to 0. And I've got to come up with the equation of this line. What is it? -x. Yeah, and we can, pretty easy here, right? We can see that because we can see the y-intercept. Okay, what if that boundary were someplace more inconvenient? We already know the answer. It's y equals -x. But what if the boundary, just hypothetically, were like here instead? So I wasn't really, I didn't have that part of the graph. What could I do? Okay, I just need, right, exactly. I would just need to come up with a point and a slope that I could plug into my new point slope formula, right? So I would pick two convenient points. Like, for example, I could pick, maybe this point right here with coordinates -2, -2, and this point right here with coordinates -3, -3. I could calculate a slope. -2 minus -3 over -2 minus -3 equals 1. So I got my slope. I could take the coordinates of a point and plug those into slope intercept, right? So y minus -2 equals 1 times x minus -2, right? And I would just get y plus 2 equals x plus 2, subtract 2 from both sides, and get, we got negative x. That shouldn't have been that, should it? I don't know. You guys probably didn't say that. I don't know why I wrote it down. What is the slope of this line? 1. So then what should that equation be? Just plain x, yeah. Right. Okay, give me thumbs on all that stuff we just did. So if it's not convenient, just use point slope. Find 2 points, calculate a slope, use point slope. Okay, what about the blue one? What's the domain? What's the blue domain? What's that doing? Oh, is it doing something weird here? There we go. What's the domain again? Sorry. Greater than 2, the domain for the blue piece? Greater than 0, right? Remember, don't get, it's easy to that's everybody makes that mistake from time to time. But remember, domain, you're thinking about the x values, right? So it's going to be x is greater than 0. And what's the equation of that horizontal line? Y equals what? Yeah, so what goes there? 2. Okay, give me thumbs. Okay, questions? Any questions? I mean, at this point, probably it's a matter of just getting some practice in to get your questions answered. Let's look at one more thing here. How do you do this on Desmos? Okay, do you really have to do it on Desmos? Not very often, but you can. You can. I want to show you how. So there's a scheme for doing this, and I thought I built something better than that. Just give me 1 second here. Let me peek ahead here. Yeah, okay, here it is. So on Desmos, here's the way Desmos wants you to input this. So you can't really build a function that looks like this conveniently in Desmos, where you've got 3 separate rows when you're inputting something. In Desmos, you kind of just have 1 row per function. So what you do is you break it into the pieces and you input them this way. So again, we'll color code these. We'll make the top one red. We'll make the middle one blue. And the bottom one green for our purposes. And then here's how that would translate. In Desmos, you would open up a set of, you would just do f of x equals, you're going to open up a set of script brackets, because this is a script bracket, right? I guess that's why they use the script brackets. And then you're going to put that stuff in, but they kind of go backwards. Like for the red piece, they want the domain first. So the domain would be what? X is less than or equal to -2. Then separating the domain for one of the pieces, so one of the rows, separating the domain from the actual equation is a colon, right? So you'd put a colon there, followed by the equation for the first piece, which is what? 2x. Okay, so then I've got my 2x. When I separate the individual pieces, I put a comma to separate the individual pieces. So what would come next, do you think, in blue? Okay. Yeah, and the nice thing about Desmos is we can write this compound inequality out so it looks exactly like that. That's convenient. So -2 less than x less than symbol 4. What comes next? Colon. And then what? There you go. -1 minus x. Now what? Comma. Good. To separate. There you go. X is greater than or equal to 4 colon -3. Okay, and then don't forget at the end, and I think it'll already be there. I think when you open up, when you type in this first script bracket, it automatically puts a second one there. So you can't really forget that, but that's what it should look like. Okay, let's do this once, just so you can, because I want to show you a couple little tricks in Desmos. It's not that big a deal. I think it's right here. Okay, so let's go through this process. You guys told me what to write, but just for grins here, why don't you tell me again? Good practice. What do I write first? F of x equals. Okay, but what do I put first? Script bracket. There you go. Notice it opens up two of them. So now I've got top domain, which was x is less than or equal to 2, right? How do I type that now? I can go down and I could pick out right there, there's a button for it. But I always prefer, it's quicker and easier to just use the keyboard if you can. How can I put in less than or equals to in Desmos, do you suppose? All I do is type less than and then an equal sign, and it knows to lump those together. It's pretty smart. So less than or equal to -2 colon 2x, comma, good, -2 is less than x less than 4, colon, -1 minus x, good. Next, comma, okay, good, x is greater than, equal to, combines them, 4, colon, -3. Okay, let's see how that looks. Okay, that's pretty good, but that's not as good as our graph. What's it missing? Yeah, the endpoints, right? So what's bad about this, the weakness of Desmos is it doesn't really tell you where the closed endpoints are. There's a way to fix this though. In Desmos, this is what I always tell students to do, so you get a little better picture. I can go down here and just open up a couple ordered pairs. So if I open up an ordered pair, what's one x value I'm interested in knowing about? -2. So I'm going to open up the ordered pair, which I'll tell you all about tomorrow.